Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 75. We are conducting this lecture after we had two tutorial sessions in the last two lectures, wherein we were discussing about various astronomical aspects such as spatial and spectral resolution, and also the concept of line of sight, column density, and number density. Now, in this lecture, I'm actually pretty excited to teach you about some new aspects of astrochemistry. See, for a major part of this course, we have been concerned with detecting molecules in space, right? By space, I'm talking about the interstellar medium. So from here onwards, so from this lecture onwards, from lecture 75 onwards, we shall finally, in fact, if I may say it in a tongue-in-cheek way, move beyond the ISM, that is the interstellar medium itself, and look at other aspects of astrochemistry. Okay, so that is what we shall be looking at from this course, from this lecture onwards. But I must also, explain something to you. Why did we spend, see, this is a course roughly containing 84 or 85 lectures, 84 or 85 half-hour lectures. But until lecture 75, starting from lecture 1 to until approximately lecture 72 or something, why did we spend an inordinate time on the interstellar medium? And why relegate, the other aspects of astrochemistry to only about like 10, 11 or 12 lectures max? What is the reason? It is that the interstellar medium is the source of everything else, if you think about it. Interstellar medium is the source of all the molecules as part of any other aspect of astrochemistry. Right? So this is one point. The other reason is that you cannot see what molecule is there in the ISM, correct? Right? Obviously, the ISM is way beyond our physical reach. I can say it, it's a triumph of the scientific enterprise. It's a triumph of the scientific method, right? Detecting molecules and proposing reactions in the interstellar medium is a huge triumph of the scientific method itself. Scientific method. And this involved a lot of fundamental science. So this involved a lot of fundamental science, including physics, chemistry, and various branches of it. I've already given you a list. It involved branches ranging from inorganic, organic, and physical chemistry. You had thermodynamics, you had spectroscopy, you had quantum mechanics, you had statistical thermodynamics, and you also needed a knowledge of classical physics. So many branches of fundamental science came together to understand what the ISM, the interstellar medium, is, and how we can detect molecules and propose various reactions which lead to the formation of these molecules. All right. So that's why the interstellar medium and its understanding, right, took up a lot of lectures. But from here onwards, we'll be looking at some other cool aspects of astrochemistry. So to begin with, we shall be looking at the chemistry of asteroids, meteorites, meteorites, comets, and planets. Of course, we can't exhaustively discuss all the aspects. We shall be looking at key aspects of the chemistry associated with all these celestial aspects. All right. Now, one very key distinction, between the chemistry that is proposed in the ISM versus the chemistry that is part of the asteroids, meteorites, comets, and planets, etc., is that from all these different sources, that is from asteroids, meteorites, comets, and planets, the biggest advantage that we have vis-a-vis, the chemistry of the ISM is that we can get physical samples. So from these, physical samples. All right. So we can get the physical samples from these objects. But then, when we talk about, say, a dense molecular cloud, or, some diffuse or dense molecular cloud, or a giant ionic cloud, or anything that is part of the interstellar medium, of course, we can detect the molecules, but we can never directly, get the samples from the interstellar medium itself. Well, yeah, you're right to think that in some cases, the asteroids and meteorites, comets and planets, they're also formed from the interstellar medium in one sense, okay? But excluding the part that is actually associated with the asteroids, meteorites, comets and planets, right? From the interstellar medium itself, we don't get sampled directly. We only have to study the molecules present in the ISM via the interaction of light with matter. From the asteroids, meteorites, comets and planets, we can directly get the physical sample. Please note this as a very important distinction. Are we good? Okay. I insist again, I repeat carefully that, of course, you're correct that, all of them have interstellar origins. Okay. Your asteroids, meteorites, comets, and planets, they of course have their origin from the interstellar medium. They're all formed from, either the formation of a star or during the collapse of a star. If you go back to lectures 4 and 5, okay, where we discussed about how these entities are formed. But whatever is left over, whatever is not part of asteroid, meteorites, comets, and planets, they are still going to be part of the giant molecular clouds. And it is detection of those molecules that was extremely challenging. And that is what required a lot of, branches of physical sciences coming together to do this cool task of detecting molecules in space. Are we good? Okay. So now, having understood that we can get physical samples from these celestial objects, we'll proceed further. Okay. Now, the first thing we shall be looking into is the chemistry of asteroids, meteorites. Okay. Now, asteroids, what are they and how are they formed? Well, I'm not going to repeat myself again now. You can actually go back to lecture 4 or 5. Okay. So, how they are formed. From so you can get this information, from lectures 4 and 5. I've already categorically and clearly told you how asteroids are formed. Basically, they are the debris, as part of the formation of a star. Okay. So the next thing is there is some important jargon here. Okay. Yeah. What is an asteroid? Well, an asteroid is it's a rocky solid body. That contains quite a lot of inorganic material that comes out of the giant molecular clouds, right? The giant molecular clouds as a protostar is getting formed, right? So that is what is an asteroid. Okay. In general, an asteroid is something that orbits around a star. In the case of our Milky Way galaxy, we're talking about the sun. So that's an asteroid. But then, what happens is that an asteroid, once it actually no longer merely orbits the sun and it comes, it like reaches the Earth, okay, right? Before reaching the Earth, it becomes what is called as a meteor. It is mostly a part of an asteroid, which reaches the Earth's atmosphere. Now, typically, we keep hearing about shooting stars. Lots of shooting stars, a range of shooting stars, which can be seen in the sky. So, the shooting stars are nothing but the meteors. So, these are the shooting stars. Okay, so this is a meteor. The point is, before an asteroid becomes a meteor, prior to entering the Earth's atmosphere, we are now limiting ourselves to the solar system, okay, our own galaxy, Milky Way, and the solar system. And we understand that we're talking about the asteroids which are orbiting the sun. That's where we start from, okay? We're not concerned with the other galaxies, etc., hereafter. So prior to entering the Earth's atmosphere, when it is called as a meteor, right? The asteroid is actually called as a meteoroid. In other words, it's en route to becoming a meteor. So we get a meteoroid. Okay, so the exact sequence should more correctly be an asteroid, becoming a meteorite, and that becoming meteor. Okay, but notice that I've said a part of an asteroid, because what happens is that it's not a complete asteroid. Asteroids are very heavy. It's only a chunk of an asteroid that even reaches the Earth's atmosphere, because due to various processes, the rocks get broken, literally. That's what happens. Okay, so that's why the asteroids first become a meteoroid, and whatever happens to enter Earth's atmosphere is what is called as a meteor. And from a meteor, whatever falls on the Earth, okay, so meteor, whatever falls on Earth, whatever part of a meteor that falls on Earth is what is actually called as a meteorite. Please note this point, okay? So it's a meteorite. We talk about, some rocks falling on the Earth, right? On the Earth's surface. That is what is called as a meteorite. So this is the distinction between asteroids, asteroid, meteoroid, meteor, and meteorite. Okay, I mean, I've written it in a haphazard way, but I think the understanding is clear enough. All right, please note this. This is important jargon just to clearly distinguish between what a meteoroid, a meteor, and a meteorite is. Now, what are famous examples of meteorites? Well, lots of meteorites have been there, but one particular meteorite that has been very widely assessed is what is called as the Murchison meteorite. Okay, an example of a meteorite, a famous example, I would say, is the Murchison. Now, Murchison is a place, apparently it's a place in Australia, which is where this meteorite fell. So that's why it's called as a Murchison meteorite. It fell approximately in the late 1960s, okay, maybe 67 or 69, okay, 67 or 69, I'm not sure, okay. So around that time, the meteorite fell, and it has been heavily analyzed by various, astronomical bodies, okay. So this is one example of Murchison meteorite, and for a long time, the largest meteorite that fell on Earth was, I think, called as Hobie. This is from Wikipedia knowledge, okay, right? Which fell somewhere in Africa, if I'm correct, Tanzania or something like that, okay. So a lot of meteorites do fall on Earth. In fact, meteor showers are pretty common. So we are constantly facing a lot of meteors and meteorites falling on Earth. But most of them, they are small in size. So they're not going to be that harmful. Okay, when I say harmful, the fall of a meteor, the probability of a meteorite falling on Earth and completely breaking off, completely shattering the Earth or causing damage, that is very low. Okay, so typically meteorites are objects which come from all the way, from being an asteroid, and they give us a lot of information. In fact, they present us with a lot of material to study the astronomy, of the various objects, the rocks, the chemistry of the space. Okay, I'm sorry, I was a bit unclear, but what I wanted to convey was that the meteorites present us with an amazing opportunity. They give us the physical samples themselves, okay, because they are the physical samples. So they give us a lot of information. What sort of information? Well, we're talking about chemical information about the constituents that are part of the meteorite, and there's a lot of scope, therefore, to understand chemistry that is happening in the rocky solid bodies. Okay, all right. So meteorites can be further generally classified in the following ways. So a meteorite can be classified broadly, into three types. Stony, you have the iron, and you have a mix. So in the stony meteorite, the rock material is predominantly, a lot of silicates. By the way, this is a broad classification. In fact, the meteorite taxonomy, that is the classification of meteorites, is a very active area with people, creating many more classes. We are just interested in a broad classification. So for our purpose, this should suffice. Okay, so the stony meteorites contain a lot of silicates. The irons contain a lot of nickel, iron, and some other heavy metals. And by the way, it is not that there are no metals over in the stony class. It is just that they are less in percentage. Whereas in the case of the irons, the metals are heavily dominant. Okay, and a mix which contains metals and the silicates in approximately equal amounts. Equal amounts of the metals and silicates. So what I've written here is equal amounts of metals and silicates. Now, the stony meteorites, right, can be further classified. I'll tell you why this is interesting. Okay, so the stony meteorite can be further classified into two major types. They are the achondrites and chondrites. Now, the distinction between achondrites and chondrites is as follows. Now, in the chondrites, you have fine, a grainy material called as chondrules. Fine, grainy, you can say almost a pebble-like, okay, kind of. Okay, I mean, I'm being very vague and qualitative because we're not doing a strict quantitative classification. Okay, please note this. So fine, grainy, and pebble-like substances called chondrules. Now, the key thing, about the chondrites is that the chondrites are, they're all formed from some sort of a molecular cloud, right? Some sort of a giant molecular cloud as a protostar is getting formed, correct? Now, the chondrites retain most of the structure. In other words, structurally, they don't undergo much change as they fall on Earth, okay? So notice that structurally, they don't undergo much change influence their formation? So please note this point about the chondrites. So therefore, the chondrites, you can assume that ever since they were generated from the interstellar, generated as interstellar debris until the time when they have fallen on Earth, right? Structural changes are very minimal. Okay, so they contain information. The chondrites therefore contain information about how the planet itself has formed, how the planetary system, how the solar system is formed, etc., etc. Okay, so the chondrites contain information about the early processes. See, when I say they contain, I'm saying that by analyzing the chondrites, we get this information. Okay, that's what I mean by they contain early processes involved in the formation of the solar system itself. All right, because their structure hasn't changed much ever since they were formed right from an interstellar debris, right? So they retain a lot of information due to the lack of any visible structural change. But in the case of the achondrites, I'll write down, I'll call them C, and I'll call this AC. AC referring to achondrites and C referring to the chondrites. Okay, but your AC, that is the achondrites, actually, they are, typically what happens is they undergo structural change as they encounter other planetary bodies. For example, some of the achondrites may have come as a result of a clash between this achondrite and some sort of a planetary body such as Mars or Jupiter or something like that. Okay, so they undergo structural changes from the time they were born. I'm using the phrase born very colloquially, okay, right? To until they hit the ground. They literally when they hit the ground, okay? And and these structural changes occur as a result of collisions between various celestial bodies. So this structural change typically happens due to also, collision is one reason. Another reason is, some strong magnetic field or some very strong radiation, right? All of these can change the structure, right? But the chondrite structure predominantly is retained. And a lot of the stony material, close to, approximately 85% of all the stony meteorites are actually chondrites. So this is roughly 85%. And this is, in the vicinity of 10%, okay? So, see, these are ballpark, so they may not add up to 100. So don't ask me why they don't add up to 100, okay? Please note this. All right, so these are the key aspects about the classification of meteorites. Of course, like I alluded to earlier, this is a very broad and general classification, and just be familiar with the names, okay? Achondrites, chondrites. And if you notice, I'm not going into great detail in terms of saying what all molecules are precisely there, because whole lot of molecules, adsorbed onto the silicate surfaces. For example, it is not just a rocky inorganic surface. Like we discussed in lectures 4 or 5, I request you to go back to those lectures, and you can see that inorganic material is also going to be associated with a lot of organic content, okay, right? Or a lot of organic molecules which are formed in several stages. See, they can be formed from the giant molecular clouds, or as the asteroid separates from the giant molecular cloud, and then as it becomes a meteoroid and a meteor to a meteorite, right? in any stage, right, a lot of these organic molecules could be formed. And I've also told you that, some very surprising molecules, such as, for example, glycine, which is a fundamental amino acid, even that has been detected, in some of these meteorites, notably the Murchison meteorite. Okay, so this is as far as the classification of meteorites is concerned. Now, the next thing that we shall be looking into is, okay, but how do we decipher what molecules are there as part of the meteorites? Even though I need not give you a complete and exhaustive list, it's important to understand. So how do people arrive at what is the composition of a meteorite? By what technique? For example, we use spectroscopy to detect molecules which are far away in space by simply obtaining light from them and comparing with spectra obtained on Earth. Well, in the case of meteorites, we already have the sample. This is again spectroscopy that is used. So how are we going to understand the composition of the meteorites, and what is one critical information that the meteorites teach us about the age of the universe, our solar system, etc., etc. So those are the aspects that we shall be looking into the next class. Okay, so to sum up, in this lecture, I introduced you to the idea that we can think beyond the interstellar medium, and we can study about the meteorites, asteroids, comets, and planets, the chemistry therein. So we started off with what an asteroid was and how the asteroid becomes a meteorite to a meteor and a meteorite as it eventually lands on Earth, and that the meteorite can be further classified into 3 types, wherein one particular classification, the stony meteorite, can be further classified as chondrites and achondrites. All right, so some other aspects of meteorites we shall be discussing in the next class. Thanks a lot. Have a good day.